Hey guys, so for my students, this is our very first remote lesson, so good luck. For anyone watching this, please feel free to contact me with any questions or feedback. Thank you. So, the overall topic we're going to start with is something called vectors, okay? And today we're going to cover the basics of this subject. So just what are vectors? Well, one way you can think about vectors is they're just arrows. So arrows like, here's a vector, there's a vector, there's another vector. So you might ask, why are we learning about arrows in math class? Why do they matter? Well, it turns out that in a lot of areas in math, science, technology, etc., these vectors, these arrows are actually pretty useful. In fact, in some situations, they're pretty fundamental. For example, anytime you've got things moving in 2 dimensions or 3 dimensions, you could say you're dealing with vectors. So to illustrate really quickly, here's an example. Let's say you have an airplane flying through the air. So here is a top view of an airplane, okay? We can represent various velocities, as in the speed and movement of the airplane, with vectors. So the jets of the airplane, the jets are blasting and it tries to make the airplane move forward like so, right? So here's what we call a velocity vector for the airplane. However, let's say there's some strong winds blowing this direction. Okay, so the velocity vector of the wind is an arrow going this way. What that's going to do, the velocity of the airplane is trying to push it forward, but the wind pushes it slightly to the side. So what you have is you have two vectors adding together for a total motion of the airplane kind of veering off the side like so. So that's an example of where you might use vectors. So now let's talk about the specifics of vectors, okay, the nitty-gritty details. So first off, the parts of a vector. So here's your vector. And first of all, what you should know is how we name vectors. So let's say this is called vector v, right? How you would label it on paper is you'd label it with a v, but with a little arrow over it, like that. So vector v. Now, the arrowhead part, we call the head. And then the bottom over here, you could say where the vector starts, we call the tail. And so sometimes we do want to think about it as starting over here and ending over here at the head, starting at the tail and ending at the head. So we can also call the tail the initial point, and then this arrowhead where the head is, we call the terminal point, terminal meaning end. And then another important feature of vectors is their length. So this vector, its length is like this distance right here, right? And let's say the length of this vector is 5. So here's a vector with length 5. Just know that the length of a vector is also called its magnitude, also called its length. And if we're labeling this as vector v with an arrow over it, then we also label the length is a number, we label that with the same v with an arrow over it, but with double vertical bars on either sides, kind of like an absolute value. So we've got the magnitude of a vector, and we said our vector here has magnitude 5, right? But something that goes hand in hand with the magnitude is the vector's direction. Now you might say, okay, the vector's pointing to above and to the right, but we got to be more specific than that, right? More precise. And so how this works, how the direction of a vector works, is you say the tail you can think of as like the origin, and then the angle works the same way you might have learned with trigonometry in like an Algebra 2 class, for example. Specifically, you think of 0 degrees as being straight to the right, right? So here's 0 degrees. And then for the direction of the vector, you ask yourself, well, how many degrees is it counterclockwise from 0? So start at 0, and then counterclockwise, you go this way. I'm going to say that's around 53 degrees. So again, what we have here, vector v, is a vector with magnitude 5 and direction around 53 degrees. Now let's talk about some more quick examples of directions of vectors. Okay, so we have two other vectors here. And remember, the direction of a vector, right, we think of it as, okay, the origin being at the tail of a vector, and then 0 degrees is always straight this way, 0 degrees. And then for the sake of example, let's say this vector, so going counterclockwise, the direction of this vector is like here, right? If you remember from your past courses, how we measure angles. And clearly it's more than 270, so for the sake of example, let's say this vector has a direction of 300 degrees. So this vector going down and to the right, again, this vector we say would have a direction of 300 degrees. Now this other vector here, we would say the origin is kind of like here, and then 0 degrees would be over here. And then its angle going counterclockwise, so like this. Now this is a straight line, so again from your past work, clearly this angle would be, this vector would have angle 180 degrees. And so again, just some examples of angles of vectors. So this magnitude and direction is useful, I think, when we're talking about vectors casually or when we're trying to visualize them. So for, again, this example of this vector being length 5, let's say, and having a direction of 53 degrees around, we said. 53 degrees. And that's fine for our understanding, but when we're talking about doing a lot of technical math, sometimes it's more beneficial to be thinking about this vector in a different way. And this different way we call component form. In other words, we want to think about the components of this vector. So what is this component form? So again, we imagine the vector starting at the tail here and going to the head. And we actually think about this vector as two numbers. It's like, well, if this is the origin, how would I get to the head like I would with a point? You've learned about points, right? So from the origin, how much would I go to the right horizontally? So if in our example the length is 5, let's say we're going right 3, and then you ask yourself, after going right 3, how much would I go up to get to the head? So like this. And again, if the length is 5, this should be about 4 right here. Okay, so we say 3 and 4 are the components of the vector. And in component form, we say, okay, this vector v, its components are 3 and 4. So we say this equals angle bracket, the horizontal component first, so 3, and then the vertical component next, 4. And you know, it's a lot like just dealing with points, right? Like you've graphed points like 3, 4 before. And in some sense, that's exactly what we're talking about. A vector can also be thought of as a point. So that's component form. One more thing, you will also see component form written like this. So we say equals, and we'll get to this more. Right now, it might look overwhelming, but we'll get back to what this means in a later lesson, okay? But this can be rewritten as 3 times the vector I plus 4 times the vector j. So that's two different ways of writing the same vector v in component form. And it turns out this component form is easier to work with certain types of things we'll be doing with vectors, easier to work with compared to working with the length and the direction. Now here's some more quick examples of component form, okay? And again, we think of the tail here as the origin. So we're thinking of that as the origin of like a graph, right, of coordinate axes. So what you have to be careful of with these components is positive and negative directions. So for example, from this tail, we go over to the head, right? And maybe we say, okay, horizontal component, we go to the right. Let's just say that's 6. But if you think about it on a graph, if you start in the origin of the graph and you go right, going right is what? The positive direction for x, right? So we would say, okay, we're going positive 6. The horizontal component is positive 6. But now for the vertical component, you see how we're going down. That's 6. Let's say this is 8. If we're going down 8, that length is 8. But as a component of a vector, we must say, okay, that component is negative 8. So then let's say this is called vector W. We would say, okay, vector W is the vector positive 6, negative 8. Now what about this other vector? It's going straight left. So its origin we think of as being here at the tail. And to get to the head, we just go straight left. So its horizontal component, let's say that length is 5. So we're going 5 to the left. And again, if you recall on a graph, if we go left horizontally, that's the negative x direction, right? So its horizontal component is negative 5. However, how much do we go up or down in going from the tail to the head? Well, we don't go up or down, right? So it's kind of hard to label on the diagram, but we say the vertical component is 0. So then if we say the vector is called vector r, we would say, okay, the horizontal component is negative 5, and the vertical component is 0. So 2 more examples of component form. So that's the basics. For our example vector here, again, we have magnitude and direction 5 and 53 degrees, and then compare that with its component forms, positive 3, comma, positive 4. And so that's 2 different forms that we can think about with vectors as we deal with them, right? And now here's the mathy part of this lesson. It's the last part, but it's the mathiest part. What we need to do, of course, is to convert between these forms. How do you start with one and get the other? So now we're going to move on to doing actual calculations, right? The mathy part, like I said. And, I feel like we've covered a lot. And so, I might like pause the video here and take a break or something because we've covered the basic concepts. Now we're going to take those basic concepts and see how we do math with them. Start out going what I think is the easier way. From component form, so starting with component form and going to magnitude and direction. So here's an example of a vector in component form. Notice there's no diagram because we need to know what these numbers mean, right? So let's say that we're going to start the vector here. Let's say that's the origin. And this has a horizontal component of positive 7 and a vertical component of negative 12. So think about what that means. Positive horizontal component means it's going right? So maybe like right 7, positive 7. And then it's going down 12, right? Because negative direction vertically is down. Like so. Now those are the components. The actual vector starts at the tail here and then goes diagonally to the bottom right? So this is our actual vector right here. Now to find the length is this length right here, right? And if you notice, this triangle is a right triangle. Like 7 is totally horizontal, this negative 12 is totally vertical, so this should be 90 degrees right here, right? And so in a previous class, you should have learned how to find the third side of a right triangle given the other two. That's the Pythagorean theorem, right? So let's label this third length of the variable x. All we got to do to find the length, we know it's a right triangle, so we can use the Pythagorean theorem. And the Pythagorean theorem c squared equals a squared plus b squared. Just remember which length goes where. The hypotenuse, or the longest side, the side across from the 90-degree angles, in this case x, goes where the c is, right? So x squared. And then the other two sides, either one can be a and the other one can be b. So let's just say positive 7 is a squared plus. And then this negative 12, yeah, it's a negative length, which is weird. But in this case, the squaring of b, right, b squared, that makes it so the negative doesn't really matter. Anyway, negative 12 squared. Now we have x squared equals 7 squared is 49. Negative 12 squared is 144. So you have x squared equals 193. And how do you get the x by itself? How do you undo squaring? Well, you square root both sides, and you get x as the square root of 193 in exact form, or as a decimal approximation, 13.89. So that's the length of the vector. It's just a straightforward application of the Pythagorean theorem. Now let's find the direction of this vector. And direction's always a little weird. Technically, we're trying to find the direction here, right? Like 0 is this way. Going counterclockwise, we're trying to find this angle right here. But it gets a little messy. And so what I would do is, first of all, just think about this angle on the inside of the triangle touching our origin here, right? We're going to name that theta. And now if you do that, you can use basic trigonometry, which I hope you've learned in a past course, to figure out that angle. Because this is a right triangle, we can use SOHCAHTOA, right? Sine, cosine, tangent. Let's see which sides we have. We have this negative 12 is opposite. So then this 7 is not the hypotenuse, so it's adjacent. And then you can set up a trig equation. Which one, sine, cosine, or tangent, uses opposite or opposite and adjacent? That's tangent. So you say, okay, tangent of theta is opposite over adjacent. You're going to go ahead and keep the negatives and positives the same. So opposite is negative 12 over adjacent is positive 7. And then to get theta by itself, you want to undo that tan. You want to cancel that tan. And how do you do that? Take the inverse tan of both sides. And here's where it gets tricky. These go away. You get theta is the inverse tan of negative 12 over 7. In my calculator, don't forget to use the right mode, I get negative 59.74 degrees. And here's the tricky thing. Sometimes you will get the wrong answer because of this angle messiness over here. Now think about it. 0 degrees is this way, right? 0 degrees. Our answer is saying negative 59 degrees. So I would always encourage you to do a sketch, because our sketch tells us actually negative 59.74 is a correct answer. And if you recall, multiple angles can mean the same thing. So negative 59.74 is a possible answer for this, right? Because we're starting at 0. Negative means we go clockwise. And that, that looks about 59 degrees. And our sketch is more or less, close to accurate. So if we're going counterclockwise this much, this answer telling us 59 degrees here, that is correct. What you have to be careful is sometimes when you do this, you will get an angle that is wrong for this vector, but correct for a related vector. So like for tangent, maybe you get an angle for the vector that goes the other way. And I'm not going to tell you like a set formulaic way to figure it out. What you really need to do is sketch a diagram and really think, what does this angle that I've gotten mean? And then, try to logic out the diagram where the angle fits. And sometimes you can use the angle that you get. Well, so if the angle that you get is not the answer, then you should still be able to use the angle that you get in your diagram to figure out the correct angle. So again, this is a correct direction for our vector. Now, negative angles are a little weird. So note that there are plenty of other answers, right? There are infinitely many angles that mean the same thing as this negative 59. If we're going counterclockwise this way, 59 degrees, sorry, clockwise that way, then going counterclockwise, you could do like 360 minus 59.74, and you will find that positive 300.25 or 26 degrees is also a valid answer. So the direction of a vector, there's actually many, many different ways you could say it. Now let's convert the other way. So now let's take a vector where we know the magnitude and direction and try to figure out the components of that vector, right? Put it in component form. And I have to apologize. Earlier I said going the other way was easier, but I think you'll find that going this way is even easier as far as the steps go. So here's an example. It says, consider a vector v with, and remember that what that means. Now I use double bars, but some people use single bars, and that means the magnitude, right? So vector v with magnitude 24 and direction angle 130 degrees. Find the component form of v. So what is v going to look like if we rewrite it like this, right? Now, I would like you to really understand what's going on. So length or magnitude 24 and angle 130. If we say the origin is here and 0 degrees is here, well, where's 130? So it goes 90 and then not quite 180, so around here. Our vector is going to look something like this, right? Here's our vector right here. And then the length is 24. So there's our vector right there. Magnitude and direction angle. And you can use trig and figure out like, okay, well, this 130 degree angle is kind of weird, but we could like extend the line here. And then do an imaginary line here to get our right triangle there. And then we have that the hypotenuse is 24. And then if this is 130, we have 50 degrees here. And again, you could do trig on it. So like the horizontal component, let's say, is x here. And the vertical component is y here. And you could set up two SOHCAHTOA equations to figure that out, right? But actually, in this situation, the angles always work out cleanly so that there's just a formula you can use that is a shortcut of all that SOHCAHTOA stuff. And so here's the formula. And I really don't like giving shortcuts like this. But in this case, the trig is, you should know it. A lot of work that's just the same every time. And again, the angles work out cleanly. We don't have to mess with like, okay, where did this angle come from? You just plug the angle into this formula and it all works out great. You could probably even derive this formula on your own. So how do we use this formula? Well, this vector that we have over here, v, right, equals bracket, and then what does this like absolute value looking thing mean? And that just means the magnitude, right? So 24, and then cosine. And this formula theta just means the angle of the vector, so 130 degrees, comma, and then again, this absolute value looking thing, that's just 24, and then times the sine of that angle, 130 degrees, close bracket. And so this is the horizontal component, comma, this is the vertical component. And if you stick these in your calculator using degree mode, of course, then you'll get that the vector is around negative 15.42 or 43 if we round. And this part, positive 18.38 or 39 if we round. And so this is that same vector in component form. And it should make sense because in our sketch, it's going from the origin, we would go left and then up, right? Positive. Negative 15 for left, positive 18 for going up. So that's the basics of vectors. Hope it all made sense. And feel free to contact me with questions or feedback.